All right, so today we're going to pull back the curtain and explore the AI factory, what it really takes to build the massive physical infrastructure behind the brains of modern AI.
Welcome to the AI Factory podcast. We're going to be talking about the incredible machinery that's really driving this whole AI revolution and, break down how it all actually works.
When you use something like GPT-4, it honestly feels like magic, right? It can write, it can code, it reasons with this incredible fluency. But behind all that magic, there's this massive physical reality. And that's really our central question today. What does it actually take to power these digital minds?
So to even begin to answer that, we have to wrap our heads around the sheer scale of the challenge we're talking about.
Okay, let's just throw a number out there to give you a sense of this. 16 terabytes. That's the estimated GPU memory you'd need just to hold all the working data for a hypothetical trillion-parameter model. I mean, think about that. That's all its knowledge, all the calculations for training. It's just a staggering amount of information.
And that number, that 16 terabytes, it leads us to a fundamental wall. The truth is, modern AI models have physically outgrown the memory of any single processor out there. You can't just go buy a bigger chip. This problem it can't be solved by a single machine, no matter how powerful it is.
So what do? Well, the solution required a total paradigm shift. It meant creating a whole new class of machine, the dedicated AI supercomputer, or what we now call the AI factory. A great example of this is something like the NVIDIA DGX SuperPod. And look, this isn't just a bunch of powerful servers stacked in a rack. It's a fully integrated system where thousands of GPUs, crazy fast networking, and specialized software are all woven together to act as one giant computational entity. The whole data center essentially becomes one single computer.
Okay, so how on earth do you get thousands of individual chips to act like one cohesive brain? Well, the answer lies in this really clever concept called parallelism. It's basically a whole set of sophisticated software tricks designed to split up this enormous workload.
All right, so the simplest way to think about this is something called data parallelism. Imagine you have an army of chefs and they're all cooking the exact same recipe. Each chef, or in our case, each GPU, gets a full copy of the AI model. But they each work with a different batch of ingredients, a unique slice of the training data. They're all working at the same time, in parallel, and then they kind of average their results together to update the main recipe. It's fast, for sure, but the catch is that every single GPU has to have enough memory to hold the entire model.
But what happens when the model is just too big to fit on one GPU? That's where pipeline parallelism comes in. And for this, think of a factory assembly line. The AI model itself is broken up into these sequential stages, or layers. So one group of GPUs handles the first few layers, then it passes its work down the line to the next group, and so on. This is the method that makes it possible to train these truly colossal models that we see today.
And then, for the absolute biggest models, we get into an even more intricate method, tensor parallelism. Now here, we're not just splitting up the model's layers, we're splitting up the mathematical operations within a single layer. So a gigantic calculation gets broken down into smaller pieces, and each GPU computes just one part of the puzzle. This is absolutely essential for getting peak performance, but man, it requires incredibly fast, almost instantaneous communication between the GPUs.
But here's the thing. Building these AI factories isn't just about throwing more and more hardware at the problem. It's also about making the models themselves more efficient. Working smarter, not just bigger.
This quote here, "All the weights are not created equal," it points to a really key optimization called unstructured sparsity. See, as a model trains, it learns which of its internal connections, or weights, are the most important. And it turns out that a lot of these weights end up being really close to zero, meaning they have very little impact. So you can actually remove them, prune them is the term, to make the model smaller and faster without really losing much accuracy.
Another really clever trick is called quantization, which uses new data types like these microscaling, or MX formats. The best way to think about it is like compressing a super high-resolution photo into a smaller file. You're representing the model's parameters with fewer bits, and that can reduce the memory footprint by 2, even 4 times. And since performance is so often limited by how fast you can pull data from memory, a smaller model is, pretty simply, a faster model. And that idea of efficiency brings us to another really smart architecture, mixture of experts, or MO. Now, instead of one single giant model that does everything, an MOE model is made up of many smaller, specialized expert networks. A sort of traffic cop mechanism sends each incoming task to only the most relevant experts for the job. And what this means is that only a fraction of the entire model gets activated at any given time. This massively increases throughput and makes it way easier to parallelize the work across different GPUs.
So this relentless quest for more and more computational power, well, it doesn't happen in a vacuum. It has enormous consequences, everything from real-world costs to some seriously intense global competition.
Just look at the hardware space. The demand for these AI chips has sparked this fierce competition. In this benchmark, for example, we're looking at text generation speed, basically how many word pieces or tokens you can generate per second. And you can see that AMD's MI300X is actually outperforming NVIDIA's H100 here. Now that's likely because it has higher memory bandwidth, which is super critical for these kinds of tasks. This competition is great for innovation, but it also really highlights the multi-billion-dollar stakes in this hardware race.
But the cost isn't just financial. The environmental price tag is, well, it's staggering. Just to put it in perspective, training a single GPT-3 model, and that's an older model now, consumed nearly 1,300 megawatt-hours of electricity.
Okay, now let's scale that up. According to one projection, if you had 1.5 million AI servers running at full tilt all day, every day, they would consume over 85 terawatt-hours of electricity in a year. That's more than the entire yearly consumption of some small countries.
And to bring that energy use down to something even more tangible, the carbon emissions from training just one of these large AI models can be equivalent to the entire lifetime emissions of 5 cars.
So here's the crucial point, the so what of all this. The immense cost and the sheer complexity of building and running these AI factories creates this formidable barrier to entry. And what that does is it concentrates the power to create these foundational AI models into the hands of just a few massive tech companies and powerful nation-states. It's creating a potential global divide between the AI haves and the AI have-nots.
Which, of course, brings us to the horizon and the big question of what lies ahead in this relentless race for more compute.
We've seen how these AI factories are becoming the new engines of progress. They're almost like critical national infrastructure at this point. And as they get bigger and more powerful, and as that power gets concentrated into fewer and fewer hands, we're really left with a pretty profound question. Who gets to decide how this incredible power is governed and how it's used?
So if this whole topic, the architecture, the geopolitics of these massive systems, is interesting to you and you want to dive a lot deeper, I really recommend checking out the book AI Factory, Architecting Global Supremacy. We've put a link for you right in the description. Thanks so much for joining me.